Hi, I'm Scott Vaughn. In this video, we'll look at writing functions as power series and finding the radius and interval of convergence. And this is video part 2. The first one is writing a power series in this form. And I'll just scroll through here and have you take a look at the other things that I was planning. Alright, so let's go back to the first question. So it's the form that I have this 9 over 1 plus 16x squared, and I want to write that as a power series, and because it's close to this 1, or let's say a over 1 minus r, it's close to the sum of a geometric series. That's one of these first beginning tools that we can use to build series. Of course, that doesn't work for everything, but it will work here. So it's because we can rewrite it in that form. So this right here becomes like this value in the geometric series that we could call r, and 9 is the a value in my geometric series. So that's the sum of a geometric series that's convergent, and this is only true when the r value is less than 1 in absolute value, and that's key. So that has a big impact on the radius of convergence of our final answer. So you see I have a times r to the power n when I start at 0, or if I started at 1, I'll use an n minus 1. You could use either way. What's happening is that once we get into power series, we very often start at 0, because as a power series, in that form, you have this constant term, then an x term, then an x squared term, an x cubed term. So this is kind of the typical thing that we would write power series starting at 0. And we were writing it starting at 1 when we were doing geometric series, just because that's the way it naturally developed at the time. So you could use either way, but being in a power series, it's often I'll often have n equals 0 as the starting term in a power series. So I have here's the a and here's the r, and now I'm going to simplify this. So I really have negative 1 to the power n, and this is 4 squared, so that's 16 to the power n, and then x to the power 2n. So this is really it as an infinite series, but because of the question, the way it was stated, it'll be useful to write out a few terms. So here's the n equals 0, n equals 1, plugging in 2, and plugging in 3. So if we say C0 is the coefficient of the x to the 0 term, then the C0 is 9, right? It's 9x to the 0. There is no x to the 1 term, so this will be 0. So I'm writing the series in this form, then I can see that it's C0 is 9, there is no x term, the C2 is negative 144, there is no C3, the C4 coefficient is this 2304. Now there was a little more to the question. It also asked us to find the radius of convergence. So to find the radius of convergence, since this was the r value in this particular derivation, this has to be less than 1 in absolute values. So that's what I'm writing here. And now we'll try to figure out how we can express that a little bit more. We'll try to figure out exactly what does that imply as the radius. So that means 16x squared is less than 1, or x squared is less than 1/16th. Which means that the x value has to be between negative 1/4 and 1/4. So that's the radius, 1/4. Okay, let's move on to question number 2. Question 2 says, write the function f of x equal ln of 1 plus x as a power series in this form from n equals 0 to infinity, c sub n, x to the power n, and write out the first 4 terms. Find the radius and interval of convergence. What we can do here is we just build a few series based on the convergence of a geometric series, and it's really limited in how effective that is, but it is effective for some particular cases. It has this very important restriction on the radius of convergence. That r value has to be, the absolute value of the r has to be less than 1. But even this function, it may not be apparent right away that you can use the geometric series, but in fact you can, because the ln is an antiderivative of 1 over 1 plus x. It's all based on the fact that the antiderivative of 1 over 1 plus x with respect to x is the ln of 1 plus x. So what I'm going to say here is that normally we put the plus c on this side, right? The antiderivative of 1 over 1 plus x with respect to x would be ln of 1 plus x plus a constant. But of course it doesn't really matter which side of that equation you put the constant, and it's convenient to write it on this side because I'm trying to expand this function. So it would be a plus c, and then it would just be a different plus c on the other side of the equation. Well, the trick is, of course, 1 over 1 plus x, we can write that as 1 over 1 minus some quantity. So that minus x becomes my r value in the geometric series. So it's always a times r to the power n. And so that's what I've done. I've replaced this 1 over 1 minus r with this infinite series with the first term a equal to 1 and common ratio negative x. Now again, I have to say that this is equal only if that absolute value of x that the absolute value of negative x, if it's less than 1, then this equal is valid. This equality is valid. You can replace this function with this infinite series if the absolute value of negative x is less than 1. So that is, x is less than 1 in absolute value. So at this point, I actually do the integration of this infinite series, which actually is pretty straightforward because actually that's what's so valuable about the power series. Power series is just, in this case, powers of x, and we're integrating with respect to x. So it's just the power rule, and it's very easy to find an antiderivative. That's why this will be so useful for other things later. The negative 1 to a power n is a constant, and here I'm just using the power rule, adding 1. So I get n plus 1, then I divide by n plus 1. And what's happening here is that I know that this has got to be true for all x that satisfy x's less than 1 in absolute value. That is everything from minus 1 to 1. So it would have to be true at 0. So 0 is convenient because both of these quantities go to 0, right? The ln of 1 plus 0, that's the ln of 1, and that's 0. And when you put 0 to a power 1, you get 0. And every single term will be 0. They'll all be 0. 0 plus 0 plus 0 plus 0 forever is 0, plus this unknown constant. But if this is really equal, then you have to have 0 equals 0 plus c, which means the c value had to be 0. So we could write it this way, starting at 0. So we actually recognize that actually if you plug in n equals 0, you get x to the 1. So the first term's actually x. It isn't a constant. So it's an alternate way of writing it this way. And this is, in fact, actually, if you look up in the Stewart book, it's an n minus 1 here, and these are both n's, and it starts at 1. So even that's another way of writing it. Whether you write n minus 1 or n plus 1, you'll get the same signs, plus and minus signs. So yeah, this is the ln of 1 plus x written as an infinite series, and it was just convenient this time to actually start at 1, because I know the first term is just x to the 1, and there is no constant term. So now we can actually write it out, a few terms. And that's just kind of an interesting pattern, right? An alternating series, x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th. And it's a very simple pattern, but specifically equal only for x. We've derived that this is true for x's less than 1 in absolute value. I can actually go back later here and check both endpoints to see whether, because we did an integration, I know the radius will stay the same. So the radius of convergence is still 1, centered at 0, but the endpoints could change, and so we could check whether or not it might converge at either of those endpoints at minus 1 or 1, and I will get to that. So here I'll just say that it's approximated by the first 4 terms, and it's certainly true for those values of x between minus 1 and 1. So let's just take a look at the graph. So here's a picture of ln of 1 plus x, and I'll write out those first few terms. And in that interval from minus 1 to 1, this blue curve seems to be a pretty good match to the red curve. So let's try more terms, adding like the first. There's 13 terms. We'll push it up further. It's kind of neat to see how it's converging. And it seems really, so, I mean, there's no evidence here whether it converges at 1 or not, but the question did ask for the interval of convergence, so we will have to check both endpoints, -1 and 1. So let's test x equal 1 and see whether or not it converges. So I'm going to put x equal 1 right into this. Now that's a convergent series by the alternating series test, right? It's alternating. You've got the terms 1 over n in absolute value that are going to decrease and go to 0. So this converges by the alternating series test. Notice, though, that it is conditionally convergent, because if you did get rid of the alternating sign, you have the harmonic series. You have 1 over n, and that diverges. So it's kind of neat to see now that if you actually write out these terms, it's an alternating series, 1 minus a half plus a third minus a fourth plus a fifth, and it will converge to this value. So now we actually have another way of finding, rather than looking at the sequence of partial sums, we're actually looking at actually writing this infinite series as a function, and we can evaluate that function. If you plugged in 1, what would you get? You get the ln of 1 plus 1. You get the ln of 2. So this is the equal to the ln of 2, but it is a conditional convergence. What that actually means is that if you actually change the order in which the terms appear, it would actually potentially be any value. So it's a kind of a weak convergence, but it's a convergence that in this particular order, as we continue to get larger and larger partial sums, it will get closer and closer to this value of ln2. And because this is the order that it's actually computing it, we can see that coming out in the calculator or on Desmos. So let's take a look at that. So here's the ln of 2, about 0.693, and I'm going to type in, so you can see by plugging in the first term, n equal 1, you get -1 squared. So the first term is 1 over 1. So the first term is 1. And then the next term, when you plug in 2, you have -1 cubed over 2. So you have -1 half. So it's kind of neat to see here I am adding up more and more terms of this alternating harmonic, and it's converging on the ln of 2, but the interesting thing is that it is alternating above the actual value of 0.693, and then below it, and then above it, and below it, and it's getting closer and closer by actually popping up and down above and below the actual value. That's a particularly interesting topic that I would like to come back to in another video, but I won't delve into that whole story right now. But the situation that you're converging with an alternating series, you can make some really interesting conclusions about the error in any approximation of the infinite series. So here I can see it popping up and down between 0.68 and 0.7 and getting really, really close to that 0.693. So I just want to add more terms, have it go up to 100 terms. It's still below. It was 0.68, and then it's right there, it's just a little bit below. So it was a little bit below, then a little bit over, and a little bit below, and but it's getting closer and closer to the ln of 2. So now if we check -1 back in that same infinite series, you can think of what's happening here is that you have -1 to an odd number. Right? So -1, always odd number there, it's always going to stay -1. So this is just like the harmonic series, but every single term negative. So it diverges for the same reason that the harmonic series diverges. And since the harmonic series we know diverges to plus infinity, we could say that this is diverging actually to minus infinity. And it just happens also that if you put -1 into the ln function, if you put -1 into this function, ln of 1 plus -1, you get the ln of 0, which is undefined, but we know that it is approaching minus infinity as you get close to that x equal -1 point. So it's diverging at -1 and it's converging at +1, so the interval is from -1 to 1, not including the -1, but including the positive 1. So here's just testing that out, looking at increasing numbers of terms in this alternating series. And then that's just taking the computer too long to figure out, to compute all those terms. So I'll just back it up to 50 terms, and there it fills it in. And okay, let's move on to number 3. What we want to do right here is we've got this function f of x equal 3x times the ln of 1 plus x, and we want to write that as a power series in this form, c sub n x to the n, and we're going to write out the first few coefficients and find the radius of convergence. So we just did the power series for ln of 1 plus x that was valid on this interval from -1 to 1, or with a radius of convergence of 1 centered at 0. So let's use that. So let me back up and just mention that if I want to drop the index down to 0, then I need to add 1 to each of these places where n occurs. So this goes from n plus 1 to n plus 2, from n here to n plus 1, and of course that n becomes an n plus 1. And I'm doing this just so I can follow this sort of figuring out what is each of the coefficients starting at 0, C0, C1, and so on. And so now the thing that we can do is say, well, what happens when you have -1 to a power n plus 2? You could think of that -1 to a power n plus 2 as actually -1 to the power n times -1 to the power 2, which of course -1 to the power 2 is positive 1. So that drops out. So that's why I can take that -1 to the power n plus 2 and just replace it with -1 to the power n. So now we can actually multiply, just 3x times this infinite series. Now this only works if this is convergent. That's the only time you can multiply these two together. What's happening is I'm saying that if this is a convergent infinite series, I can treat it as a number in any arithmetic involving multiplication, division, addition, subtraction. I can do the math with this as if it were that number to which it converges. So what we can do here is if these are constant, so what's happening is the 3 and the x are constant in the series, because the series is based on n. N equals 0 to infinity, so you're just distributing that x to each term, and it's constant. It doesn't change. It doesn't depend on the value of n. It's independent of the value of n, and so you can just multiply it in. So x times x to the power n plus 1 just gives me x to the power n plus 2. So this is writing it out as an infinite series. It's convenient to have it in this form, I want to say. For example, if you're testing for convergence. It's also might be useful if I see what I'll do here is I'll take ln of 1 plus x and actually write it out term by term, and that's another way of sort of doing the multiplication and seeing that we have it right. So it's easy to see here why all the powers go up by 1. I'm just multiplying this through to each term. And plus ... it goes on forever. So there is no x to the 0 term. There is no x to the 1 term. So the whole thing really starts with a coefficient C2, which would be 3, right? And this is the coefficient of the x cubed term. C3 is -3/2, and so on. 1 is the coefficient of the degree 4 term. And -3/4 is the coefficient of the x to the 5th term, and 3/5 is the coefficient of the x to the 6th term. Now, we want to find the radius of convergence. So the radius of convergence was r equal 1 for the function that we had here, this ln. So that remains the same radius of convergence when you multiply it by this 3 times x. It doesn't change the convergence. So multiplying by a polynomial here, we're not changing the radius or interval of convergence for the new series. So it's the same interval and same radius that we had. Let's go back and take a look at the graph. We'll just take the first few terms here. So here in the graph I have 3x times ln of 1 plus x is the red curve, and these 5 terms, 3x squared minus 3/2 x cubed plus x to the 4th minus 3/4 x to the 5th plus 3/5 x to the 6th. What's significant here is that I've got an approximation for this ln function all in terms of a polynomial, right? A polynomial approximation for this transcendental function, which is really a useful tool for lots of things, as we'll see as we're finishing off this course. I mean, this one more question I have at the end, number 4, we'll begin to suggest how that could work. But there's many more ways in which this is used than I'll be able to get into this one video. So here's just a picture of the two curves together, and you can see that they're pretty good fit there between -1 and 1. Okay, so now I want to move on to number 4. I want to write an infinite series for f of x equals sine of x squared. So we'll start off with this infinite series for sine. So I won't derive it here because that will take a while, and I'll leave that for another video. So what's really pretty neat about this is that the sine will converge for all x, and so the interval of convergence is -infinity to +infinity. The radius, we would say, is infinite, the radius of convergence for sine of x. One of the things that sticks in my mind about this is I've already kind of got it in memory that the sine is an odd function, and I can see that visually by its shape. And being an odd function is sort of one of the little clues that helps me remember it's all these odd powers divided by that odd value factorial, and it's alternating. That's how I remember it. So if we're going to do sine of x squared, this is just amazing how what we're saying is this is true for any value of x. And that's even if that x was equal to some quantity x squared, right? If the x was x squared, or if x squared was the x. So you just replace x squared in for x. It's amazing, right, that works. So you see how all I did was I just replaced the x with x squared. And that was it. Now I'm going to simplify this, so I'm just going to multiply 2 times 2n plus 1. That's going to give me 4n plus 2. Everything else stays the same. Alright, so that answers part A. Now let's get the first 4 terms of the series approximation. So we'll just write out the first 4 terms of this and graph both the original function f of x and the series approximation on the computer or calculator and compare them. So what are the first 4 terms? So what I'm doing here is just plugging in 0, 1, 2, and 3. So when I put in 0, I have -1 to the 0. That's positive. That's just a 1. Putting in n equals 0 here, I get x squared, and n equals 0 here, I just get 1. So the first term is just x squared. Next thing is I plug in 1. So that's 4 plus 2. That's where I get 6. Over, of course, plugging in 1, you get 3 factorial, and 3 factorial is 6. So the next thing is this was n equals 0, n equal 1. Now I have n equal 2. When you plug in n equal 2, that's 4 times 2. That's 8 plus 2, that's 10. So we have x to the 10. And we're plugging in 2, so that's 2 times 2, that's 4 plus 1, that's 5. 5 factorial, that's 120. And of course I'm plugging in 2. So I have a -1 squared, which makes it positive. So I recognize as I'm going to go through this that I just keep alternating signs. So I know the next one's a negative. And I'm plugging in, this is 0, 1, 2. So I'm plugging in 3. Plug in 3, that's 4 times 3, that's 12, plus 2, that's 14. So I have x to the 14, and then I'm plugging in 3 here. So that's 7 factorial, that's 5040. So that's the first 4 terms. Let's take a look at the graph. So back to Desmos. And the first thing I want to see is sine of x squared. And I'm most interested in this interval between -1 and 1. So let's do this. And now what we had was x to the power, let's see. It's just cool to watch this thing develop as you type it in. It's just amazing. Yeah, so that does look like a good match for that function, sine of x squared, on that. Well, actually, ultimately, this will converge anywhere, but it seems very accurate between -1 and 1. and then it's no longer fitting. But if the more terms that we add in this case, we know that this one will converge for all values of x. Just that the fact that it's centered at 0 means that it's more accurate near 0 with fewer terms, and it would take more terms to be that accurate at values further from 0. It's possible to rederive this thing so that it's centered at some other value. So you would need fewer terms at a different point or near some other point. But so this is centered at 0, so it's most accurate there. It takes fewer terms to be accurate near 0. Okay, so and one of the significant things here I'll getting to at the end of this video now, at the end of these examples, is that quantity there, that function sine of x squared, is something that at the beginning of Calc 2 we had no way of integrating that. It is impossible to write an exact antiderivative for sine of x squared. The only way to do it is some kind of an approximation, and so this is one of the approximating methods that we can do it, is with this infinite series approximation. The infinite series is exact, so we would say, I'm saying this series approximation, this is a finite series that's an approximation for sine of x squared, and I can get an approximation for the antiderivative with as many terms as I choose, and the more terms I have, the better the approximation, right? So part C says use the first 4 terms to find a series approximation for an antiderivative of that function, right? So the antiderivative sine of x squared, there was nothing at the beginning of Calc 2 that would have found there is no way to get an exact antiderivative, but we can approximate it now because we have this tool. That's one of the basic tools of what series are for, is these approximations. They are and particularly useful because we can integrate the polynomial. It's easy. So actually what I'm going to do is an integral of this whole entire thing. So actually this is really easy. If you're integrating this thing, all you have to do is just go with power rule. So you're going to get x cubed over 3, and then you'll have x to the 7 divided by 6 times 7, so it puts a 42 on the bottom. Well, I'll write it this way. What I'm trying to say is that I want to integrate this function here, and that is an approximation to the antiderivative of sine of x squared. So we can go through this term by term and integrate. So x to the 3 over 3, it's just the power rule. This is going to be x to the 7 over, now you got 6 times 7, so that's actually 42. And then integrate this one, that's x to the 11 over 120 times 11, and that's 1320. And now we've got x to the 15 power over 15 times 5040, 75,600. And we'll put plus c because this is the general antiderivative. So there's not part C. We can find an antiderivative for that function, and then we can use that now in part D. Use the series approximation to find the area bounded by f of x equals sine of x squared and the x-axis on the interval from -1 to 1, and round to 4 decimal places. So this will be, so let's just say we'll take the antiderivative and plug in the bounds. Oh, hold on a second. Actually, because I've got a -1 and a +1, and I have this function that I know is an even function, right? It doesn't matter whether you plug in negative values or positive values, you'll get the same result because of that square. What we could do is we'll say it's exactly equal to 2 times the integral from 0 to 1. You don't have to do that, but it's convenient. That way I only have to plug in 1. When I plug in 0, it'll be easy. It'll simplify easy, right? So I prefer plugging in 0, so I'll take advantage of that. So it's exactly equal to this integral, and then this we'll just say is approximately 2 times, and now we have an antiderivative for this guy, an approximate antiderivative right here. We're plugging in 0 and 1. And plugging in 0 is easy. So this is equal to 2 times. And plugging 1 into all these values, I get 1/3 minus 1 over 42, 1 over 1320, minus 1 over 75,600. And then, of course, minus 0. So let's see what that is. That's 0.6205. So here in part E, sketch the function sine of x squared and shade the region corresponding to the above integral. So that is from minus 1 to 1, sine of x squared. And compare the answer with the numerical integration done by the calculator and write that answer from the calculator to 4 decimal places. So to 4 decimal places, it's 0.6205, exactly the same thing that we just got doing it with a series approximation. Okay, so that's the end of the video. Hope it's been helpful. Thank you for watching.